Welcome back. In the last class, we discussed various things about scalar couplings and we started discussing about signs of the couplings. Remember, I mentioned about the sign of the coupling, especially how to arrive at the sign. We started looking at first important thing by Dirac model. What is the sign of a one bond CH coupling? We understood because it is the orientation of the one of the magnetic moment of one of the nucleus, if you consider it of the coupled ones, like proton and carbon, if they are chemically bonded. If you see the orientation of proton spin, if it is in the direction parallel to the field, because of this Fermi's contact and Pauling pairing and again Fermi contact, using this Dirac model, this orientation forces the carbon to orient in a direction anti-parallel to it. As a consequence, I said this is lower energy state and stable and it corresponds to energy state. In such a way, the J coupling is greater than 0. That means 1JCH is always positive. And we also worked out 2JCH, that is negative. We also worked out 3JCH, that is again positive. In a simple model like this, okay? We worked out based on the orientation, the nuclear magnetic moment of one of the protons or one of the nucleus, which is of the CH bond, and then proceeded further from a Fermi contact, Linus Pauling here, and then again Fermi, Linus, like that we went through the various bonds, all the three bonds, and we arrived at the coupling, a sign of the coupling, and we found out 3JCH is positive. That's fine. Now, how does the spectrum look for positive, negative sign of the coupling? So, as I said, CH coupling is positive on 1JCH and 2JCH is negative. Suppose I take a spectrum. In one case, let us the sign is positive. In the other case, I will say sign is negative. How does the spectrum look? That let us understand. Now I consider a situation, two coupled spins. Maybe it is a CH coupling, carbon and proton. Doesn't matter. We consider a situation, one bond carbon proton coupling. We know J is positive for it. And if I consider the spectrum, assume a situation, both carbon 13 is also highly, it is abundant in the sense label system. In which case, I look at the proton, I get the 2 peaks. I look at the carbon, I get 2 peaks. It is a AX spin system, 2 lines for proton, 2 lines for carbon. Now I am plotting one next to each other. This is for A spin, proton, this is for X spin, carbon 13. In our energy level diagram and all the splitting pattern, we understood when two protons are two nuclei are coupled, homo or heteronuclear does not matter. From the energy level diagram, we observed you get 2 peaks for A and 2 peaks for X of equal intensity. Okay. Now we also worked out based on the transitions how this transition takes place between two energy states, which spin is flipping. We also found out which transitions pertains to A spin, which transition pertains to X spin. Both we understood. So that's how we identified two A transitions and two X transitions. I hope you remember the energy level diagram with which we worked out transitions for both A and X. Let us say this is the pattern I am going to get for J greater than 0. Most important, you have to monitor A1, A2, X2, X1. These are the numbering I have given for transitions A and transitions X. That we know. Transitions we have already worked out. Consider the situation. Now J is less than 0. That is J is negative. What is the difference you are seeing here? Except because I have colored for to make you understand, you will not find any difference because in the real spectrum, when you record 1D spectrum, there is no coloring of the transitions. Just to make you people understand, I made one transition of A, one transition of X has different color. For J positive, J greater than 0. Now J greater than 0, if you look at the spectrum, you see A2 has come here, A1 has moved here. You understand? X1 has come here and X2 here has moved here. So you understand A1 and A2 got interchanged here and X1 and X2 got interchanged here. Fantastic. But if I don't color it, if I don't tell you anything, you will not know which transition is which. Because you don't go and find out by the energy level diagram every time. Simply I'll give you a spectrum with J greater than 0. I'll give you another spectrum with J less than 0. And I'll give you independently both of them. You will not find the difference. You will find everything is overlapping the way it is. Only thing is internally lines like this would have interchanged with change of sign. Remember what? Look at this. It is two lines are like this. They get reversed. That's all. A transition gets interchanged between the coupled spins, but you will not find any change in the appearance of the spectrum apart from that. So as a consequence, the spectrum is invariant with respect to the change of sign. If the coupling is either positive or negative, from the one-dimensional spectrum, it is not possible for you to find out. So the splitting pattern is independent of the sign of the couplings. Please remember that splitting pattern is independent of the sign of the coupling. So one-dimensional spectrum, as a consequence, will not give you idea about the sign of the couplings. Please remember, one-dimensional spectrum will not give you information on the sign of the couplings. But there are some experiments we can do. You do not know the absolute sign of the couplings, but we can find out the relative sign of the coupling. You know what it means? I already told you 1 bond JCH is positive. If I have a spectrum with carbon proton and coupled, I measure couplings. I know 1 bond JCH is positive. With respect to that, I can measure the sign of other coupling in some experiments. It is possible. So it means I will not be able to find the absolute sign of the couplings in NMR spectrum. Only I can get the relative signs of the coupling. That's first point. Second, spectrum is invariant, remains invariant with the change in the sign of the coupling. These are the things. So one-dimensional spectrum cannot give information on the sign of the coupling. For this, you need to do some special two-dimensional experiments. Now, before we go further for analysis of the spectrum, so far I was talking to you about chemically inequivalent protons coupling, where one coupled to 2 protons, 3 protons, and we have arrived at the family tree way of multiplicity pattern. But there are examples where there are chemically equal groups of spins will be there. For example, there is a CH3 group, there may be a CH2 group present in the molecule, or it may be CF3 group with the 3 fluorines equivalent like CH3 may be present, CF2 may be present. Like that, some groups will be there, group of chemically equivalent spins will be there. That also we need to understand to get into the information about the splitting pattern. And before that, remember when I introduced chemical shift, I told you about chemical equivalence based on the symmetry operation. I wrote symmetry axis and said this proton is equivalent to this proton is equivalent to this in chemical shift. But at this there in that slide, I also told you there is a J coupling information which was at the bottom. I highlighted and said I will discuss this later. That is the thing now we have to discuss. In the chemical equivalence, the chemical shifts are equivalence. Now think of a situation. You have a molecule. There are molecules which are chemically equivalent. There are spins which are chemically equivalent. But there are several spins which are coupled among themselves. You understand my question? In a molecule, chemical shifts may be equivalent because for certain protons. But it may so happen the couplings may also be equal. What happen? Why not? Why it cannot be? It cannot happen. It can also happen. Why should it not happen? There's a possibility. In addition to chemical shift, J coupling can also become equivalent among coupled spins in some cases. Then we bring in another term called magnetic equivalence. In a chemical equivalence, we discuss only chemical shift being equivalent based on the symmetry operation. But in the magnetic equivalence, in addition to chemical shift, J couplings also will be equal. This is your example. We'll look at it. So magnetically equivalent nuclei have all their chemical shifts are same. In addition to that, they have identical scalar coupling constant to other coupled spins. Very important statement. So, in the case of magnetically equivalent, chemical shifts were only equal, but magnetically equivalent nuclei have same chemical shifts, they're equivalent, but at the same time, couplings to other coupled protons are also same. That is magnetically equivalence. Say, for example, I have three spins. Okay. Now I will take the three spins, 1, 2, and 3. Now what is happening is J12 in this case, maybe all the three protons, let us assume chemical shift is, okay, chemical shift is same. It has to be chemically equivalent. I'll take the highlighter. Okay. Sorry. I'll take the highlighter. Now you see what happened. It's here. Okay. So now three protons are there. This proton, and this proton are all having same chemical shifts. I call it delta 1, delta 2, and delta 3. Now, I also say coupling between 1 and 2, J12, coupling between 1 and 3, J13, and coupling between 2 and 3, J23, I would say all are same. This information was not told to you before when I discussed chemical shift, chemical equivalence. Now when I discuss magnetical equivalence, in addition to chemical equivalence, I am also telling you they are magnetically equivalent because their couplings are also same. This is a very important information. So now the logic is simple. All magnetically equivalent nuclei are chemically equivalent. Remember, all magnetically equivalent are chemically equivalent, whereas converse is not true. If I take all magnetically equivalent nuclei, like this one, delta 1, delta 2, this one is there. That means they have to be invariably chemically equivalent. But if this is equivalent, it need not be equivalent. That is a reverse case. That is chemically equivalent. So concept is, remember, very simple. All magnetically equivalent spins are invariably chemically equivalent, but all chemically equivalent spins need not be magnetically equivalent. It's an important point you must understand. Now look at the examples of magnetically equivalent spins. Look at this molecule. Does it have a symmetry axis? If you look at it, there is a symmetry axis here along this axis. So chemical shift of 1 is equal to chemical shift of 2. Okay. Chemical shift of 1 is equal to chemical shift of 2. Nu 1 equal to nu 2. What is coupling? This coupling is equal to this coupling. J13 is equal to J23. What does it mean? Chemical shifts are also same. Coupling of these spins with all other spins are also same. That means these protons are magnetically equivalent. You understand? These protons are magnetically equivalent. Now look at another example. What about this molecule? There is a symmetry axis along this, right? Now chemical shift of 1 is equal to 2. All the three chemical CH3 protons are equivalent. All these CH3 protons are equivalent. Apart from that, chemical shift of these three protons and chemical shift of these three protons are also equal. Now this is different. There are two groups of protons, but now look at the coupling of this proton to this. Okay, very interesting thing you should observe. The coupling of 2 to 3 and 1 to 3, they are all same. J13 is equal to J23. So that means two CH3 protons are magnetically equivalent as they have the same coupling to CH proton in addition to having same chemical shifts. These two are magnetically equivalent nuclei. Look at this one. This is a fantastic molecule. It's methane. Now take any proton of your interest. This, and this. All four protons have the same chemical shift. See, nu 1 is equal to nu 2 is equal to nu 3 is equal to nu 4. That is very interesting thing. Okay. Now, What about the J coupling between this and this? J coupling between this and this, between this and this, and between this and this, or this and this. Take all the possible couplings here. Look at this. J12 is equal to J13 is equal to J14 equal to J23 equal to J24 is equal to J4. All the couplings here are equivalent. All 6 couplings are equivalent. What does it mean? For any proton, coupling to remaining 3 protons are same. Any proton you take. For 1, 1, 4, 1, 2, 1, 3 is same. For 4, 1, 4, 3, 4, 2, 4 is same. Like that, all couplings are same and all chemical shifts are same. So the methane is an example of a perfectly magnetically equivalent system. Okay, all 4 protons here are magnetically equivalent. Look at this molecule now. This is 1,4-difluoro and 2,3-dichlorobenzene. Is there a symmetry axis here? Yes. One along this, one along this. There are 2 symmetry axes. As a consequence, nu1 is equal to nu4. Fluorine 1 and 4 are equal. And proton 2 is equal to proton 3. Nu2 is equal to nu3. And what about J12? Is J12 is equal to J34. That's also true. And now J13 is equal to J24. Whereas J34 is not equal to 24. Similarly, J12 is not equal to 13. What does it tell? These 2 protons are magnetically equivalent. 2 fluorines are magnetically equivalent with multiple couplings of identical strands. Imagine, see, there can be a situation where we have magnetically equivalent, but with multiple couplings in the same molecule. Look at this one. I'll remove all these highlighters. This coupling and this coupling is same. So you can forget about the others. So you take only fluorine. Fluorine has 1, 2, 1, 3, 1, 4. 3 couplings. Okay. Similarly, you take this one. This was 3, 4, 2, and 2, 4 and 1, 4. There are 3 couplings. They are identical. Okay. Now go back to protons actually. Proton has 2, 1, 2, 4 and 2, 3 couplings. Similarly, if you take this 3 proton, 3, 4, 3, 2 and 3, 1, they are all same. So that means these 2 protons are magnetically equivalent with different coupling strength, multiple coupling strength of identical magnitude. This proton has multiple couplings. This proton has multiple couplings, but the coupling strengths, though they are different, it is same when you consider this proton and this proton. Okay, you understand what I'm trying to say? There are this 1, 2 is equal to 3, 4, no problem. Similarly, 1, 3 is equal to 2, 4. There are 2 different types of coupling, but they are same. Similarly, so you can understand 2 protons are magnetically equivalent and 2 fluorines are also magnetically equivalent with different couplings. What about benzene? It's a very, very simple molecule, well known. In the chemical equivalence, I have told you, the benzene, all 6 protons are chemically equivalent. All 6 protons resonate at the same position. And if you take the benzene NMR, proton NMR, or even carbon 13 NMR, does not matter, you get a single peak. Only one peak. That means the chemical shifts are same. Nu1 equal to nu2, equal to nu3, equal to nu4, nu5, and nu6. All chemical shifts are same. But what about their coupling strengths? Remember, now J12 is not equal to 1,3 because this is 3-bond coupling, this is 4-bond coupling, and this is 5-bond coupling. So 1, 2 is not equal to 1, 3 is not equal to 2, 4. Any proton you take, this is ortho coupling, meta coupling, and para coupling. Each proton experiences 3 types of coupling: ortho, meta, and para. Each proton. 6 protons, each proton among them, each proton has 3 different couplings. But nevertheless, ortho coupling, para coupling, and meta coupling for all the protons are identical. This ortho coupling is same as this ortho coupling. same as this, same as this, same as this, same as this. Similarly, this metacoupling, this metacoupling, this metacoupling are same. Similarly, this paracoupling, and these paracouplings are same. What does it mean? This is a situation. Each proton experiences three different couplings of identical strength. Each of these protons. So all six protons are same chemical shift. Each of them experience three different couplings of identical strength. This is what is another example of magnetically equivalent spins with multiple couplings. You understand? This is the magnetically equivalence case with multiple couplings. Now in this case what happens? This is ethylene. There is a perfect symmetry along this axis now. I can write one axis here, one axis here. This proton is equal to this proton, and this proton is equal to this proton, and similarly this is same, this is same, this is same, this is same. So all protons, because of the symmetry consideration, all are chemically equivalent. Nu1 equal to Nu2 equal to Nu3 equal to Nu4. But let us see what are the types of couplings we see. This is 1-2 bond coupling, geminal. 1, 2 and 3, this is 3 bond coupling, vicinal. 1, 2 and 3, this is 3 bond coupling, trans, vicinal trans coupling, vicinal cis coupling. But all are different strengths. This geminal coupling is different than this vicinal cis coupling, than this vicinal trans coupling. They are not same. Same for each of these protons. This has again geminal, vicinal, trans. This has again geminal, vicinal, and trans. This has again geminal, trans, and vicinal. Each proton experiences three different couplings of identical strengths. So as a consequence, what happens is J12 is not equal to J13, is not equal to J14. Again, this is a classic example of magnetically equivalent spins with more than one coupling, multiple couplings of identical strength. This is also magnetically equivalent spin. But there is one interesting thing you must observe here. All these are chemically equivalent spins. In these chemically equivalent spins, J coupling is not going to be observed. I'll tell you when we go ahead further. In the chemically equivalent case, J couplings are not reflected in the spectrum. Same, if you go back to benzene. Benzene gives a single line. But I said there are three different couplings. But why are we not seeing multiplicity? In always, in chemically equivalent and magnetically equivalent cases, the couplings are not reflected in the spectrum. You will not see the couplings. They disappear. Even though they exist. Not that coupling is zero here. Ortho meta and para couplings are present. They are not zero. But only thing is you don't see it in the spectrum. Okay, same here in this example. So, but then question is, how do I know what is the coupling? How when I say single, here also I get only a single peak. Ethylene, at 5.29, one of the chemical sheet test slides I showed you. All photons are chemically equivalent, comes at 5.29 ppm. With one peak, how did I measure all the couplings? This is a fantastic example to tell you how we can get the couplings in chemically or magnetically equivalent spins. We'll discuss this later after certain number of, or maybe after one class or two class. I'll take specific examples how we can get the couplings among chemically equivalent spins. We'll come to that later. At the moment, don't worry, but remember there are three different couplings present. You don't see in the spectrum, and four chemical shifts are also identical. So it is a magnetically equivalent spins with multiple couplings. Now, with this knowledge, let us go and look at the multiplicity of different spin systems. How when they couple, chemically equivalent groups couple, what will happen to the splitting part? This is a very interesting thing we must try to understand. Remember in this slide, when I was briefing you about the salient points of scalar coupling, I made one statement that our coupling among the group of equivalent spins is given by 2ni plus 1 rule, I said. I hope you remember. I said coupling among this thing is given by 2ni plus 1 rule. And I also said The intensities of these things are given by Pascal triangle. Intensity of the multiplied is intensities are given by Pascal triangle. That's a very interesting thing. This is the point. You remember, this is an important statement. If you have CH2 group, they are chemically equivalent to protons. And if I have a CH3 group, all the three protons are chemically equivalent. But CH2 protons can couple to CH3 protons. Similarly, CH3 protons can couple to CH2 protons. In both the cases, the splitting is given by 2ni+1 rule. And what is the intensity pattern? It is unlike chemical inequivalence, which is of equal intensity. Here the intensity patterns are different. And that is given by Pascal triangle. Remember this one, that is given by Pascal triangle. We will see what it is. But there are exceptions for 2ni+1 rule. Consider a molecule like this. There is a perfect equivalence space. This is equivalent to this. When this is equivalent, this will not give rise to coupling with this. This will not couple to this one. Same way, carbon, this will not couple to this carbon. In the equivalent case, there is a perfect symmetry. J couplings do not influence the spectrum. You understand? This is exception for 2ni+1 rule. Look at this one. If X and Y are different, this environment is different, this environment is different. As a consequence, what is going to happen? This proton splits into this, splits because of coupling with this. This splits because of coupling with this. Because X and Y are different, there is no chemical equivalence. On the other hand, X equal to Y, in this case or in this case, no problems. When X is equal to Y, there is no coupling at all. You don't have to worry anything. Simply say there is a perfect symmetry and this is a molecule. This proton cannot interact with this proton. There is no coupling. It is not seen in the spectrum. Okay. So this is the example of case where you will not be able to see the coupling among equivalent spins just by applying 2ni+1 rule. Supposing if X is not equal to Y here, what I get? If X is not equal to here, what type of splitting I get? I will now explain to you. Excuse me. Now look at the tetramethylserine molecule. It's a very simple molecule. All of you know that. When I discuss chemical shift itself, remember, when I discuss chemical shift, I explained to you this CH3, this CH3, this CH3, all CH3s are chemically equivalent. And the protons of this CH3 group are also chemically equivalent. That means all the 12 protons, we have 12 protons here, you know, all the 12 protons of tetramethylserine are perfectly equivalent, chemically equivalent, and also magnetically equivalent. Coupling between this CH3 to this CH3, this to this, they are all same. You will not see that the effect on the spectrum. That's another example to say 2ni+1 rule do not apply here. This cannot split because of this under 2ni+1 rule. This cannot undergo splitting because of this under 2ni+1 rule. These are the classic examples to show there are exceptions for the 2ni+1 rule. Now, with this idea in mind, let us start looking at the multiplicity pattern due to coupling among equivalent spins. This is now deviating from other way. Other case, we were simply seeing only one proton, one spin in coupling to other. So family chain, family tree. We started doing 1 become 2, 2 become 4. That was the ways to understand multiplicity. And at the end, all multiplicity will be of equal intensity. But now let us see what happens in the equivalent spins. In the equivalent spins, when it is there, things are different. Consider an example like this. There is only one proton, you get only one line. Now consider a situation, one proton is coupled to another proton, you get two lines. Consider a situation, of course this coupling is J1. This is well known. When two protons are coupled, we get a doublet for this and also doublet for this. This we have been discussing. Now, interesting thing is, I look at this molecule. In this case, as there is a perfect symmetry along this axis. That means this coupling and this coupling are same. J12 is equal to J13. then this undergoes splitting because of this and this together. Similarly, these two protons will undergo splitting because of this proton. You understand now what I'm trying to say? This proton and this proton splits this one together, and these two together are split by this proton. Now let us see what happens. This is an example to show that J12 is equal to J13. It is a chemically equivalent spin. So we call CH2 are equivalent groups. In this case, simply I will say proton is coupled to CH2. That's all. Look at this. It gives me a triplet. Okay? When I look at the proton 1, when it's coupled to two equivalent protons, gives me a triplet. How? We'll understand how it goes. And this separation gives me J12 or J13, does not matter, both are same, because I have written equivalent relation here. Okay, so that is the situation. How does this triplet arise is something interesting. Let us understand this now. How does the triplet come? I will start with a simple case. Without any splitting between these two, this will give a singlet. Now I'll bring the coupling to proton 2. Remember, in a family tree, it becomes doublet of equal intensity. Now the intensity has come down by 50-50. It is 50%. It divided, distribution of intensity between two members of the family. So intensity became 50-50. And this coupling is J12. Now this I will bring in the coupling to proton 3. This is alpha beta spin states of proton 2. That's why we have two orientations and doublet. Now I'll bring in the coupling to proton 3. Proton 3 also undergoes coupling, and each line will become split into doublet. So what is intensity? This is 25, here 25, here 25, and another 25 here. Because this doublet is 25-25 intensity, this doublet has 25-25 intensity. This will overlap and give rise to 50 intensity. You understand now? In this case, this is 50% intensity because two lines of this intensity are overlapped here. Why it is overlapped? Because the coupling is same. J12 is equal to J13. If J12 were not equal to J13, you would have got 4 peaks. Like a family tree approach, what we did. But because of equivalence, central two peaks are overlapped of equal intensity. So now understand this one. 100 intensity became 50-50 due to coupling with this proton, and each of them became 25, 25, 25, and 25. These two central peaks overlap, and total intensity become 25, 50, and 25. What is that intensity ratio now? 1:2:1. You understand? Don't try to get confused. Now the intensity ratio is 1:2:1. This is when two equivalent protons are coupled to a single proton, you get 1:2:1 intensity ratio. Now, this can be understood in a different logic. What is this logic? These two correspond to beta-beta orientation. And here there are two possible orientations, alpha, beta, beta, alpha. They overlap and give rise to two intensity. Now this corresponds to alpha, alpha. This is only one intensity. See, this is one intensity. This is two are same, overlap and twice the intensity. And this is one intensity. As a consequence, the triplet intensity will be ratio of 1:2:1. You understand? The triplet comes with an intensity ratio of 1:2:1 when two equivalent protons are coupled to a third spin. Now the question is, what happens to this proton? I'll ask you, what happened to these two protons when it is coupled to one? All of you should know. This is equivalent as far as When I am observing, I observe a single peak because these two are equivalent chemically equivalent spins. And now this is split by a third spin. Just it will become a doublet, nothing more. Because these two are indistinguishable. There is only one peak. You can consider as a single spin, compound spin, which splits with this one, this proton, and becomes a doublet. So in this case, if I have a situation like this molecule, like this will become a triplet and this will become a doublet. So if I take the NMR spectrum of this molecule, I'll get a triplet and I'll get a doublet. That is the total spectrum. All of you, I hope you understood. Triplet comes because of two central peaks overlap, and that is possibility of two alpha beta and beta alpha have identical energies overlapped, and this is for alpha alpha orientation, this is beta beta orientation. So this is a simple example to say when do you get a triplet? When any of the proton or group of proton, doesn't matter, it may need not be single proton, it could be CA3, CH, CH, anything. And it is coupled to equivalent spins, two equivalent spins like CH2, the splitting pattern will always be a triplet for this one. Remember, this will be always be a triplet. So this is what I just wanted to tell you about this. And we continue with multiplicity pattern, how it comes for other spin systems, like when we have a CA3 coupled, or when we have CH2 CA3 coupled, how it comes, everything later. And what happens when two CA3s are coupled, or one CH2, two CA3, or three CH2s are coupled. Varieties of examples we can take. Couple of more examples we'll take and understand how the splitting arises in the case of chemically equivalent spins. So we'll do that in the next class. Right now, for this, I am going to stop it.